Transformers can feel almost magical, but they come with real trade-offs: big compute bills, latency issues, data risks, and surprising failure modes. In this topic, you'll see where transformers break, what they really cost, and how to use them responsibly in real systems. You've already gone from what is ML to training and prompting transformer models and seeing where they shine. Now we zoom out. Before chasing more capabilities, we'll look at real-world limits, costs, risks, and trade-offs, and then point you toward your next learning steps. Most discussions of transformers focus on the shiny 20%, fluent text, cool demos, impressive benchmarks. The hidden 80% is harder to see: huge compute bills, data demands, operational complexity, and ethical risk. We'll unpack these less visible costs so you can design realistic systems and make responsible decisions about what to build and deploy. To build a useful mental model, we'll group transformer challenges into 4 buckets. First, compute and data. How much hardware and training data you need, and what that does to cost and feasibility. Second, scaling choices. When making a model bigger actually helps, and when it just burns resources. Third, ethics and safety, bias, misuse, and harm reduction. And finally, production operations, latency, reliability, monitoring, and keeping models updated in the real world. Modern transformers are hungry for hardware. Training usually demands powerful GPUs or TPUs working in parallel, not just a single laptop. As models and sequence lengths grow, their memory footprint explodes, quickly overwhelming consumer machines. Even inference can feel sluggish on CPUs, which is why many teams rely on cloud-based, pre-trained models instead. Transformers are powerful because they're trained on truly massive text collections, often billions of tokens. That's far beyond what most teams can realistically gather, clean, and label themselves. And it's not just size. The data must be diverse, high quality, and legally and ethically defensible. If your dataset is too small or narrow, the model memorizes instead of generalizing. These constraints are why pre-trained foundation models plus light fine-tuning have become the default approach. Training transformers from scratch is like running your own data center. You need huge datasets, expensive GPUs, and serious distributed system skills. Pre-trained models compress all of that effort into a reusable package. You inherit rich language knowledge, then fine-tune for your task with a smaller dataset and a single machine. Platforms like Hugging Face make this practical, so you spend most of your time designing, testing, and improving solutions, not building infrastructure. Scaling laws show that as we increase model size, data, and compute, performance tends to improve in a smooth, predictable way. The catch is diminishing returns. Early scaling gives big gains for relatively modest cost. Later, each extra bit of accuracy requires far more parameters, training time, and energy. So bigger is better only up to a point. The real question becomes, where does the added performance justify the exploding cost? Choosing model size is about fit, not bragging rights. Smaller or distilled models shine when you need fast responses, low cloud bills, and easy deployment to CPUs or edge devices. They're ideal for focused tasks like routing, classification, or simple chat. Larger models make sense when your tasks are messy, open-ended, or require long context and richer reasoning. Start small, measure, and only scale up when the added capability clearly pays for itself. Transformers don't invent bias from nowhere. They absorb whatever is common in the data they see. If certain voices dominate the training set, those perspectives become the default. That can show up as obvious stereotypes, but also as subtle patterns. Who's mentioned as a leader, whose errors get excused, whose don't. Because these models run at massive scale, even small imbalances can quietly turn into automated system-wide unfairness. Transformers need defense in depth. We don't rely on a single safety switch. We layer protections across the lifecycle. We start by filtering and curating training data to reduce harmful patterns. Then we align the model with human feedback so its default behavior is safer. At inference time, we add prompt guardrails and output filters. Finally, organizations monitor usage, define red lines, and update safeguards quickly when new misuse patterns appear. Putting a transformer into production introduces two major pain points: latency and memory. Long prompts and big models mean slow responses and huge VRAM footprints. So we aggressively optimize. Quantization shrinks weights. Pruning removes redundant connections. Caching avoids recomputing repeated parts of the sequence. Distillation trains a smaller student with similar behavior. In many real systems, a well-distilled smaller model is what finally makes the product usable. Transformers don't stay accurate just because they were well-trained once. Language, user behavior, and regulations shift, and the model's assumptions quietly go out of date. So you watch for drift, track error rates, complaints, bias patterns, and odd edge cases. Then you feed that back into updates, new prompts, new data, or a refreshed model. Treat this as ongoing operations with logging and clear ownership, not a one-time project. Working with transformers is really about deciding what you care about most. More capability usually means higher compute cost, slower inference, and more complex risks to manage. You rarely get maximum performance, safety, speed, and low cost at the same time. So be intentional. Lean on pre-trained models, right-size them for your problem, and bake in monitoring and guardrails early. As you practice on small projects, you'll build intuition for the trade-offs that fit your context. Transformers are powerful, but they're not magic. Big gains usually require big compute, large datasets, and careful scaling choices. You also need to design for bias, fairness, safety, latency, and monitoring. From here, we'll map out learning paths so you can deepen your skills and target realistic, responsible projects.